We'll start at 9 o'clock for this inaugural.
Okay, I
Yeah,
stand
and
by.
yeah, yeah. Good morning, Murali sir. Good morning, Umali sir.
Yeah, good morning to all of you.
Yeah, good
Good
morning, sir.
morning.
So,
Uh,
yeah, good morning, sir. Our chief guest has also arrived.
yeah,
He is
good.
on the board. Yeah.
Right.
So,
Right.
yeah,
Welcome,
we
sir.
are. Sir,
Good
we are.
morning.
Yeah, good morning, sir. So we are just waiting for Dr. Santosh Rane to join Dean Academics, and then we'll
Yeah,
start the
joined, I
program.
think.
Sir, I already joined. Very good
Right,
morning
Okay,
joined.
to
very good
everybody.
morning, sir. Very good morning. Very good morning,
Welcome,
sir.
warm welcome to Dr. Rao, sir, and all
Good
the
morning, sir.
participants.
Good.
Good morning.
Yes,
Yeah,
sir, yes.
yeah. So Sadhvi, we can start the function.
Yeah, yeah, go ahead.
Yes, yes, sir. Yes, sir. With each new day comes new strengths and new thoughts. A very good morning to one and all. It is my privilege to welcome you all to the 1 week faculty development program on 3D printing and design, organized by Bharatiya Vidya Bhavan, Sardar Patel College of Engineering, and sponsored by All India Council for Technical Education, Training and Learning Academy. Now, I request everyone to be ready for the Saraswati Vandana, followed by the lighting of the lamp ceremony.
शुभं कुरुत्वं कल्याणम् आरोग्यं धनसम्पदः शुभं कुरुत्वं कल्याणम् आरोग्यं धनसम्पदः शत्रुबुद्धिविनाशाय दीपज्योतिर्नमोऽस्तु ते दीपज्योतिर्नमोऽस्तु ते शुभं कुरुत्वं कल्याणम् आरोग्यं धनसम्पदः शुभं कुरुत्वं कल्याणम् आरोग्यं धनसम्पदः या कुन्देन्दुतुषारहारधवला या शुभ्रवस्त्रावृता या वीणावरदण्डमण्डितकरा या श्वेतपद्मासना या ब्रह्माच्युतशङ्करप्रभृतिभिः देवैः सदा वन्दिता सा मां पातु सरस्वती भगवती निःशेषजाड्यापहा
Now, I would like to speak a few words about Dr. K.M. Munshi, the great founder of Bharatiya Vidya Bhavan. Kanhaiyalal Maneklal Munshi was popularly known by his pet name Ghanshyam Vyas. Dr. K.M. Munshi was a prolific writer and had written many pieces, mostly involving around the Indian independence movement, Gandhian ideology, Indian culture, and mythology. Dr. K.M. Munshi was born on the 30th December 1887 in Bharuch, Gujarat. He completed his schooling in Khan Bahadur Dalal School, after which he pursued his college education in the Baroda College. He was particularly drawn by the views of Sri Aurobindo Ghosh, who was his teacher in the Baroda College. In the year 1907, he arrived in Bombay to practice law after topping his LLB and BA examinations. After completing his studies, Dr. Munshi gave into social reform and activism, especially in the areas of women's rights and caste prejudice. He also became a member of the Subjects Committee and functioned as the secretary of the Bombay Presidency Association. Dr. K. M. Munshi founded the Bharatiya Vidya Bhavan in the year 1938 with an aim to preserve the Indian culture, education, and art from a secular perspective. Dr. K. M. Munshi was an active participant in the freedom struggle. He extended legal course to a number of freedom fighters who were detained by the British Raj, and also participated in the Bardoli Satyagraha, Salt Satyagraha, and the Quit India movement. He was one of the most active members of the assembly, being a member of 16 committees and subcommittees, including the drafting committee. Some of his interventions were in the debates relating the fundamental rights,
बघतोय हे कारण आमचा
citizenship,
प्रोग्राम सुरू
and
आहे
minority rights. After independence, he served as the Minister for Agriculture and Food till the year 1953. During his tenure as an agriculture minister, he conceptualized the Van Mahotsav initiative to increase the forest cover in the country. He served as the governor of Uttar Pradesh from 1953 to 1957. In 1954, he started a monthly journal called Bhargava in Gujarati and also started the Journal of Bharatiya Vidya Bhavan that is run to this day. Dr. K. M. Munshi died on 8 February 1971 at the age of 83 in Bombay, India. Today, Munshiji's fear about cultural decadence and breakdown of value systems have indeed come true. But Bhavan, the movement, is striving to weigh off attacks and defy odds to carry forward his message and mission. Now, I would like to request Ms. Arundhati Joshi from Second Year Mechanical to speak a few words about Sardar Vallabhbhai Patel.
Sardar Vallabhbhai Patel once said, manpower without unity is not a strength unless it is harmonized and united properly. Then it becomes a spiritual power. Vallabhbhai Zavierbhai Patel was also popularly known as the Iron Man of India, as he did a remarkable job in the integration of the country by unifying 562 princely states in the newly independent country. He played a vital role in the Quit India movement and India's struggle for independence. Soon after the independence of India, he became the first Home Minister and Deputy Prime Minister of India. He said in one of his sessions, no distinctions of caste and creed should hamper us. All are the sons and daughters of India. We should all love our country and build our destiny on our mutual love and help. He always wanted to remove the distinctions of rich and poor, caste and creed, high and low from our country. Thus, he worked really hard for it. He was a true citizen of the country. To honor him, his birth anniversary is celebrated as Rashtriya Ekta Divas every year. Modern Indian history is incomplete without Sardar Vallabhbhai Patel. His vision, his work, and his principles are highly remarkable in independent India. The speeches delivered by him signify India's integrity, India's resolve, India's determination, but mostly India's unity. It shows that India was, is, and always will be eternal, truly a symbol that Ek Bharat hai Shreshta Bharat. It was Sardar Vallabhbhai Patel because of whom we are living in a united India and interacting with the world on our own terms. It was his efforts following the independence that led to the formation of India the way it is today. India was divided into small states during the time Sardar Patel took office. People thought that India could never stand united. But Sardar Patel came as a ray of hope, proving everyone otherwise. From Kutch to Kohima, Kashmir to Kanyakumari, if we can travel around the country without any hindrance, then it is only because of him. Had he not taken this initiative, then we would probably be needing a visa today to travel amongst our states. He was a selfless leader who placed country's interests above everything else and shaped India's destiny with single minded devotion. The invaluable contribution of Sardar Vallabhbhai Patel in building a modern and unified India needs to be remembered by every Indian as the country marches ahead as one of the largest economies in the world. He was a senior leader in the Constituent Assembly of India and was responsible in large measure for shaping India's constitution. Hence, he is also known as the Bismarck of India. Patel was instrumental in putting the rights of minorities and tribal folks in Constituent Assembly debates. Being a powerful orator, most of his recommendations to various articles were accepted by the members of the Constituent Assembly without any modification. Hence, later, some also referred to Indian Constitution as the Patel Constitution. His interest laid in helping the downtrodden to rise in level with the tallest in the land. He showed that mass satyagraha was no longer the idle dream of a visionary, but a concrete idea rich in potentialities. Hence, he was also known as the architect of free India. With this, it can be safely concluded that Sardar Vallabhbhai Patel's contribution to the integration of India, his vision of a newly born state, was unmatched, and none of the contemporaries could have lived up to the requirements of the time better than him. Thank you.
Thank you so much, Arundhati. Now I would like to request Dr. Kiran Bhore sir, Dean R&D, Sardar Patel College of Engineering, and the coordinator of this program to kindly welcome the participants.
Thank you, Sadhvi. Honorable Chief Guest Dr. Guru Prasad Rao, Director and Mentor of Imaginarium India, respected Principal Sir Dr. M.M. Murdi, Head of the Department Mechanical Engineering Dr. Sudhakar Rumale, and my dear participants of the program. It gives me immense pleasure to welcome all the participants for the AICT's ATAL sponsored 1 week faculty development program on 3D printing and design, which is starting from today, 20th September 2021 to 24th September 2021. 3D printing or additive manufacturing is construction of a three-dimensional object from a CAD model or digital model. The term 3D printing can refer to a variety of processes in which material is deposited, joined, or solidified under computer control to create a three-dimensional object with material being added together, such as plastics, liquids, or powder grain being fused together, typically in layer by layer manner. In the 1980s, the 3D printing technique was considered suitably only for the production of functional or aesthetic prototypes, and more appropriate term for it at that time was rapid prototyping. As of today, the precision, repeatability, and material range of 3D printing have increased to the point that some 3D printing processes are considered viable as an industrial production technology, whereby the term additive manufacturing can be used synonymously with 3D printing. One of the key advantages of 3D printing is the ability to produce very complex shapes or geometries that would be otherwise impossible to construct by hand, including hollow parts or parts with internal structure to reduce weight. Considering this immense potential of 3D printing, it is considered as one of the enabling technology of Industry 4.0 revolution. AICT has also identified the 9 prominent thrust areas, and 3D printing is amongst one of them. Considering these entire dimensions, SPC, Sardar Patel College of Engineering, also wished to conduct the FDP on 3D printing and design, and under the umbrella, under the sponsorship of AICT, we are running this particular program. For this program, we have invited experts from industry like Imaginarium, Wipro 3D, and experts from premium institutions like IIT, NIT, National Manufacturing Institute Scotland, VJTI, and so on. The first session of this program will be conducted by our chief guest, Dr. Guru Prasad Rao, Director and Mentor at Imaginarium India. Overall, the FDP is going to cover the introduction and fundamentals to 3D printing to the industrial and biomedical applications of it. I am sure after attending all sessions of the FDP, participant would be able to understand the fundamentals of 3D printing and design and its potential application in various domains. I once again welcome all the participants of the FDP and wish them for great learning ahead in this FDP. Thank you very much.
Thank you, sir. Thank you for such a warm welcome and giving us a basic overview of the program. Now I would like to request Dr. S.S. Umare sir, Head of Mechanical Engineering Department, Sardar Patel College of Engineering, to please guide the participants.
Am I audible, Sadhvi?
Yes, sir.
Yes, sir.
Thank you. Good morning to all of you. Dear participants, Dr. Kiran Bhore, coordinators, Professor Hasin Sheikh and Professor Sharad Warvi, co-coordinator of this program, Dr. Santosh Rane, Dean Academics, and Dr. M.M. Murdi, principal of this college, and Dr. Seshayar, Director, Board of Governing, Sardar Patel College of Engineering. I also thank Dr. Abhay Saheb, Director of Technical Education. I take this opportunity to welcome Honorable Chief Guest, Dr. Guru Prasad Rao, Director and Mentor, Imaginarium India. I welcome all participants in this 1 week FDP on 3D printing and design. This FDP is sponsored by AICT's Training and Learning Academy. I would like to thank all the participants for registering for this 1 week program. I would like to thank Dr. M.M. Murdi, Principal, Sardar Patel College of Engineering, and BOG Chairman, Dr. Sheshayar, for permitting to arrange this important and knowledgeable program on 3D printing. The Mechanical Engineering Department has continuously taken efforts for the interest of aspiring engineering students and meet the needs of the challenging world of business. Over the last 50 years, the department has gained an excellent reputation in the field of technical education. The curriculum of the mechanical department is based on a recent recommendation by UGC, AICT, and National Board of Accreditation. The latest syllabus is aligned towards the national competitive examinations such as GATE examinations, which is very important for students to get admission in the MTech as well as getting recruitments in the reputed industries. The curriculum promotes knowledge about Industry 4.0. The requirements of smart industry is satisfied by inclusion of courses such as IoT, augmented reality, artificial intelligence, and machine learning, and very importantly, that is digital manufacturing. The curriculum includes the comments received from Industry Consultation Committee formed by department faculty for review of various courses of UG and PG programs. We have added 3 mandatory courses of 0 credit which must be passed before obtaining degree, 5 professional elective courses groups, 3 open elective courses groups, and very importantly, value-added courses of 0 credits for additional gain of technical skills such as CNC programming and Python programming. These subjects are very important nowadays in the industries because nowadays industry is progressing towards automation, industrial automations, and hence we are adapted these courses, CNC programming and Python programming for the students of mechanical engineering. Now, examination reforms recommended by AICT are implemented. The reforms facilitate correlations of examinations questions to COs, Bloom's taxonomy level performance indicators. The faculty, particularly mechanical faculty, are using modern teaching and learning and assessment tools. Mechanical engineering department offers industry sponsored courses to students, arranging expert lectures by the industry persons, conducting industrial visits for the students, offering industry sponsored students projects to get different skills. I now want to indicate that department has started new teaching and learning methods like SWAM and NPTEL courses as per AICT directions. Mechanical students are also encouraged to work for competitive events such as racing car competitions, Robocon competitions, and other similar activities to promote their technical knowledge and skills. I personally and on behalf of Mechanical Engineering Department congratulate for this FDP to Dr. Kiran Bhole and his team. I also convey best wishes to all for success for this FDP. Thank you all for patience listening. Thank you very much.
Thank you, sir. Thank you for your kind words and enlightening us with your thoughts. Now I request Dr. Santosh Rane sir, Dean Academic, Sardar Patel College of Engineering, to kindly guide the participants.
Thank you, Sadhvi. Am I audible to all of you?
Yes, sir.
Thank you. Good morning to everybody and warm welcome to SPC. Welcome Dr. Guru Prasad Rao as the chief guest for this function. We are very happy to start this program 3D printing and design. First of all, I congratulate Dr. Kiran Bhore to put in a lot of efforts in receiving 4 such kind of training program for SPC in the various fields offered by AICT under ATAL Academy. This is the first program. Another 3 programs are going to be scheduled in due course of time. We are fortunate to receive the blessings from our patron, Dr. Sheshayar, Chairman of BOG, Dr. Abhay Vak, Director of DT, and our beloved Principal, Dr. Murdi Sir. At SPC, we have done a lot of curriculum reforms, and majority of those curriculum reforms have been already told by Dr. Umare. I'm thankful to him so that my major speech has been already covered by him. This particular 3D printing and design is one of the key areas in the manufacturing. It is going to redefine the entire manufacturing world. You can just imagine the kind of a product the 3D printing manufacturing technology is available to design and develop the product. So in the coming future, majority of the products available in the market will be through 3D printing. As I have already said, it is going to redefine the entire manufacturing world. So all those manufacturing processes which we have learned in our time will be step by step going to obsolescence. So we have to move towards 3D printing. That is the need of a time, and that's what we have to accept. So we have to unlearn some of the things and we have to learn the new things. I welcome all the participants for this entire program and give the best wishes to them to learn the new things. But at the same time, I invite the participants to get involved in the research being carried out under Dr. Kiran Bhore's guidance. The Moola mantra for the success is 20% learning and 80% creation of the knowledge, creation of the intellectual property right. That is the Moola mantra. So invest your 20% time in learning and remaining 80% of the time for creating the new knowledge, for creating the new intellectual property. If you see the QS university ranking across the globe, then there are only 3 universities of India in the top 200 list. One is IIT Bombay, ranking number 117. Another is IIT Delhi, ranking number 185, and ISC Bangalore, ranking 186. It means that we are far, far behind the world. The concept is we need more concentrated, dedicated efforts towards the value creation, the knowledge creation, intellectual property creation, and offering the necessary ecosystem for the research promotion, offering the necessary ecosystem for the education system as per the QS ranking, as per the global requirement. So there are many dimensions included in that, and we all taken together can certainly transform this situation. We have to join the hands. I invite all the participants to get connected with Dr. Kiran Bhode sir for carrying out the cutting edge research. I'm thankful to all my colleagues, Dr. Umare sir, Dr. Sabnis madam, and our honorable principal, Dr. Murudi sir, for giving the necessary support for organizing this 3D printing and design course successfully. Thanks to everybody. I wish best of luck to everybody and happy learning. Thank you.
Thank you, sir. Thank you so much for your kind words and deeply acknowledging us with your thoughts. Now, I would like to request Dr. M.M. Murdi, sir, Principal, Sardar Patel College of Engineering and HOD Civil, to kindly address the participants.
Good morning to all of you. Chief guest of the today's inaugural function, Dr. Guru Prasad Rao, course coordinator and Dean R&D, Dr. Kiran Bhole, Dean Academic, Dr. Santosh Rane, Head of the Department Mechanical, Dr. Umale, Head of the Department Electrical, Dr. Anupa Sabnis, and all my dear colleagues and participants. I am happy that the Mechanical Department of SPCE is organizing 1 week FDP on 3D printer and design, which is sponsored by AICT under ATAL program. As told by Kiran Bhole, the 3D printing and design is a very advanced and hot topic. As informed to you by Dr. Rane, I am happy to inform you all that the college has received the funding under this ATAL scheme for 4 FDPs. So this is what the first one which is going to start from today, and the same thing, I suppose it is repetition in December, 3D printing only, and 1 FDP on drug engineering by our faculty in chemistry department, Dr. Bholve, and which will be organized in October, and 1 more FDP on developing interpersonal skills and effective communication intelligence by our faculty member, Dr. Shamli Solanki. As told by Kiran, the speakers are renowned faculty from NITs, IITs, SPC, VJT, and industries. So I am sure that all the participants will definitely benefited by this FDP. I congratulate and thank Dean R&D, Dr. Kiran Bhole, and also course coordinator for taking keen interest in organizing this event. I also thank co-coordinators Hasin Sheikh and Sharad Walvi for their involvement in the organization of this course. I welcome all the participants and thank for their participation. I wish this program a grand success. Thank you.
Thank you. Thank you so much, sir, for your kind words. Now, I would like to welcome our respected chief guest, who also happens to be the eminent speaker for this session, Dr. Guru Prasad Rao, sir. With all due honors, it will be a great pleasure for me to introduce you all to our noteworthy speaker. Dr. Guru Prasad Rao, sir, is a technocrat with over 30 plus years of experience, including product design and development, business development, design research, corporate development, business operations, digital fabrication, and strategy. He is currently the director and mentor at Imaginarium India, the most diverse 3D printing company located in Mumbai. He currently focuses on life and DFAM besides technology mentoring, building Imaginarium Life, Imaginarium Academy, and technology partnerships across domains. Before Imaginarium, he was a professor at and chief coordinator at PLMCC at JSSATE, Bangalore. He is primarily focused on product design, jewelry design, and PLM. He previously served in key roles at Crompton Green, Titan, and Tanish. His specialties include 3D printing and its applications in healthcare, DFAM, general management, corporate development, product development, business operations, strategy, and product marketing. Sir will be briefing this session on the topic 3D printing and design, present and future. Over to you, sir.
Thank you very much, Satvi Chaube, for such a generous introduction. I would like to thank Dean R&D, Kiran Bole sir, for inviting me and giving me this opportunity. I would like to thank the principal, SPSC, and the HODs, electrical, civil, and mechanical, who also are, gracing this occasion. I would like to also thank Santosh Rane sir, the Dean Academics, for gracing this. And I think my job is done a lot easier by all their introduction about this wonderful technology. As a practitioner, I would sometimes agree to some points I may not agree, because I am going to talk from my industrial experience. Okay. And today's, we are going to go on a kind of memory lane of technology, capturing, we cannot talk about present and future of 3D printing and design without talking about the past, And let me try to present to you I'll try to share my screen. Let me know if you can all see my screen.
Yes, sir. Visible, sir.
Wonderful. I would like to say good morning to all of you, the participants, the faculty, some of you are researchers, most of you are assistant professor level faculty, and there are few professors also. It's a great honor for me to present the practices what we have at Imaginarium, the company which probably very maverick to start this discipline long time ago, And my own tries with this technology goes back to 90s. 86 the patent was granted, and 90 we were actually studying it in our PG. And Rane sir mentioned about, and principal also mentioned about some of the great institutes. In fact, I happen to be from IISc, and I also happen to be an alumni of IIT Bombay. Those areas, these are the institutes which started 3D printing also very early on. They got probably India's first 3D printers, to IIT Kanpur, IIT Bombay, and IISc. And in fact, I was running a mission in my alma mater IISc in the year 2000. And so it was a kind of a hands-on. I never realized that, I'll be again working on this in a greater depth, this is what we call it a destiny. And many times I keep, if I were to recollect my earlier talks, I used to also tell people that this is the future technology and this is going to replace all manufacturing. But after having, gone through this for 20 years now with this technology, I can see that this is a kind of a, not a uh, revolution, but a evolution. From 86 to today, 2021, we have passed 35 years. 35 years is such a long time, almost one third of a century is passed, and people are still talking about the technology. So there must be something right or wrong with this technology. Probably that's what I'm going to talk in my next talk. So let me not go deep into it. But today we'll stick to the past, present, and future. Well, most of the things what I use in my slide, they're all, it belongs to various people, IPs. What we own is our narrative and its organization. And, you know, the whole world, what we see today, they're all made up. It is a built world, we call. So human beings have brought something called as the artificial. Artificial means one which is not natural. Correct? No? Can I request somebody to mute themselves? There's someone who is on live disturbing me.
Yes, Mr. Professor Ranjit Patil, please mute. Ranjit Patil, Professor Ranjit Patil, please mute your mic. Professor Ranjit Patil or Kashmiri, you can have the right to mute the participant. Please mute it. Yeah. Okay,
Thank you,
sir.
sir.
Done.
So we were at how human race have come trying to build, trying to not adjusting with the nature, but modifying nature. They could have, like birds and animals, they could have stayed, in the nature without building anything. Of course, when it is raining, like right now, it is raining outside heavily in Bombay. People used to go under the tree or get into a cave, naturally occurring things. But they felt it is not adequate. There are not too many caves, not too many. Probably they had a lot of trees, but that is dangerous because animals are going to come and kill them. So they needed many things. So the human kind, has started modifying the world. Today's topic, very interestingly, they say 3D printing and design. Now, why design has been added to 3D printing? Very interesting, isn't it? Because without design, you can do nothing about it. You cannot print anything without design. And design also, what design you are going to do? Design has to address a problem, a problem which is burning, meaning prioritized. You may have 10 problems, but you elect and select one problem and you focus on it and you solve that problem. Next comes the next in the priority, right? Now, so design is a problem solving activity, and very interestingly, the organizers have added this 3D printing and design, and we'll come back to this again and again. This session would repeatedly stress about the role of design, because at the end of the day, manufacturing will be taken for granted. Believe me, the world, whatever you see, the progress comes from design, not from the manufacturing, because it will be taken for granted. Somebody will do something somewhere, and who bothers, right? Today, right now, for world, they thought so. They gave it everything to China. You design at your own countries, you give it to China, they will make it. It is least value added or value adding activity. If you look at the smile curve, manufacturing is the least value added activity. What is most value added? It is the branding, design, research, IP, all that. On the other side, logistics, networking, owning customer relationship, and all that. Manufacturing, the treasury of manufacturing, making things, managing supply chain, all that is going to be dumped. Probably, that's what America did. That's what Europe did. But the nature has a way to play the balance. The nature gave world a new challenge, the COVID, right? When the COVID was brought, it took everyone by surprise. The supply chains, global supply chains got cut. Now Europe is looking at becoming self-sufficient. America is becoming their own self-sufficiency they need to achieve. Though China is still supplying, people have realized depending on one country alone as a world factory can be dangerous after all. In India also, we have been going for self-reliance. Of course, it's always there, but now with a enhanced, underlining of Atma Nirbharata, the challenge taken up by the PM and the government, people are trying to see how best, and many countries have actually stopped working with China and they're shifting to India. Not only India, whoever, it can go to Bangladesh, it can go to Sri Lanka, it can go to Vietnam, it can go to, so there is a kind of a competition now in the, so there is a shift in the geopolitical situation. And so that is a kind of a foundation, art of making things. I'm going to zoom you into prehistoric time. The humans actually had no written communication, Language was not born. They were only imitating animals, probably. The birds. And they hunted. And they kept a record of it in the caves. They were still not ready to build houses, So they were more like animals, but little better, because birds don't keep record. Animals don't keep record, and human beings did. So that is beauty. So you have the manifestation of that in many caves, and this is one of them, one of the early ones in the France, and people have depicted the animal hunting scenes. So after the kill, they ate food. After they're happy with the filled stomach, they started writing whatever they saw. That has become a kind of a record. So this is one of the early records of human record keeping. And much later, people started to protect themselves. And human hands are kind of lousy. They don't have any long nails or claws or paws or whatever you call. We had to depend on something harder, something durable. You can see the beauty of how they adopted stone. The stones in the riverbed, they were rolling and becoming round, and the round cannot be used to cut. It can grind, but it cannot cut. So in order to cut, they actually chipped off these stones on one side. On the other side, they kept it round so that they can have a bearing area on their hand. See the beauty. The design was managing the world. Design is nothing but coping with the world, the circumstances, the context, and staying fit and to survive. All this is to survive. And they made so many of them. They also had great knowledge about using a kind of a wooden stack or stick or branch as a mechanical advantage, a lever, without knowing actually the principles of mechanics and all. They were able to have, because they were able to safely without their hands getting hurt. They extended their hand by a wooden stick, and they tied those stones, and they were able to do a better kill. So this civilization of humans happened after a long time. This is an evolution, you know and in fact, the other record keeping, time time is something, or counting and accounting. you know you can say this is a bone on which they have made some marks. People decipher this as some kind of early counting of human beings started. That's very important because we are talking about Industry 4.0 today. Computing, the mathematical things are now automated. The counting has become automated with the use of computers. So it's very important to get back to these roots where we started. And also, you can see the artifact from the top row to bottom, the top row left to bottom row right, far right. You see the artifacts having themselves a kind of evolution. The utilitarian things started appearing much later, and the decorations, the treatment, the finish, the finish, all these are something which are learned over a period of time. And today we are trying to actually look at asteroids. We are looking at moon. We are looking at Mars and beyond. People are even thinking of space travel, so much so they have gone and come, had a kind of public getting exposure to space, beyond astronauts. And people are also looking at building colonies. And probably today's technology, the 3D printing, is one of the most versatile technologies that can go into space, and also not only space, but to the heavenly bodies like probably Titan, the Saturn satellite, which has got Earth-like conditions. It has got a blue sky, and we don't know what all there inside, but it is very close to a very big, giant, poisonous planet, Saturn, and it is very, very cold there, right? But before that, they need to leap to moon and to the Mars. So, in fact, one has to travel almost at the speed of light to reach these places quickly. While it is impossible to fly at the speed of light because of various physics and related issues we have, but additive manufacturing is enabling humans to explore these long distance travel, because they're able to make things lighter. They're able to make exotic material in a most optimum way, that 3D printing can give. Well, you can see how people have progressed through the ages, making so many artifacts. So if we look at the early artifact to one which is recent, that is also 1500 BC, you can see they're not too different. They're not too different. Even today, what we use is not too different. Probably the rice they grew years back probably was more healthier than what we do today with chemical and other things. So that's why people are moving towards the organic things and all. But interestingly, the 1500 BC artifact on the right hand side has motifs which are repeated. So they were able to divide a circle. So not only they knew how to make this, but also they were able to divide it. And many have recorded many things on these. And so we are actually talking about art of making things now. And the clay which was easily available They could do many things. Along with the clay, they also got many other things, shining objects. These shining objects are nothing but metal. It could be gold, it could be copper, any other, naturally occurring metal separated from the metamorphosis rock. They also got tumbled in the rivers. They flew down the river, and the Bronze Age was marked. They soon discovered these are better tools, so they were able to make very, very fine tools, needles and all. And you can just see what all people have done in the Bronze Age. Beautiful, isn't it? They had so many uh, uh, ways to do it. The lost wax process was already known to them, you know, and so much so, even today we use it. And of course, with the iron, which is a harder material, people were able to actually make good iron in India. And that's why in India you find a lot of stone temples. And not only that, the woods steel from Tamil Nadu, that area, it went all over the world, particularly to the Damascus and Jerusalem and Greece and all that. So it was a tool material. So we were the pioneers in that, and it is a low carbon steel, giving it a cutting edge. And even today people are exploring and going beyond that. HSS, high speed steel, and all. How they have we study great deal about steel, the iron carbide diagram, and the Mar edging steel has become a great material today for tool making, and that is being explored in 3D printing. Mar edging, martensitic and aging, they combine the word, these two, martensite and aging, Mar aging steel, and they have been doing wonderful experiments on that front. But you can see some of these manifestations in the wonderful stone sculptures people see across the world. Even in the Mohenjo-daro time, there you can see, and till recently, during the Kakatiya period also, we see in the later on Vijayanagar period also, many things in Mount Abu and many places, we see a lot of such artifacts being done because they had the working knowledge with a strong material which can cut. So if we want to sum up, they started with what they could shape easily, clay, by their own hands, and then it started taking different forms. People had pinching method, people had putting a ring over the one above the other and smudging them together to make a pot, or it could be potter's wheel. And this is something which we see even today. A technology probably which is 30,000, 40,000 or 50,000 years ago. Nobody knows, because people are able to find every day new findings of pottery being unearthed, and we don't know, we went to high school and we read all this. What is happening today in archaeology and all are throwing lights that these are all very old, older than what we thought. There are some crafts which even today we use hands, like this basket. And in the early days, there was only crafted things. The markets, what we find, they were very similar to what we see. And human beings, whatever they had around the surrounding them, they started making use of them, in order to keep themselves warm, in order to protect themselves from the sun or wind. They started making many things, and so the making is something which is purely for the survival, purpose. Later on, when they could cope up with many things, they started a cottage industry. But the cottage industry is something at one's home is not very disciplined. So this is what they did, and they gave it to the weekly market, and you can see there is no consistency of artifacts here. They could make many things, but not one thing which is, millions. They could not do it, and consistency was a problem, quality was a problem, but there were a lot of always master craftsmen who could actually do very well, and others learned from it. So there was a kind of a early university of skills, like what we have now, skill sector council and all. So they were the guild, art craft guilds were there all over the world, and they were making it for their own local consumption. Even the transaction was a barter system. There's no currency or coin or whatever, and much later it all changed, isn't it? And so people in the early 17th or late 17th century, the factory was born, where people, the craft guilds, they kind of closed down, and they said, okay, we'll give you a small place where all of you come and do your work. So this was also kind of a forerunner to Ford's line system, production line, and also a division of labor. Here division of labor is not seen, but you can see people are working on their hands, in their hands, and they have supervisors who take care of their needs, raw material supply and all that. If they need anything, they are just a facilitators there. So this is the early, image of a factory without any kind of machinery, mechanization, or such things. But soon they had to improve it. The mechanization started, just like how the early humans used a wooden stick to increase mechanical advantage of stone. Many of these principles were put together to make things, to do many things. We all know this. And then, of course, the Industrial Revolution was born. It was born because of one, people who wanted to make a lot of money on one side, the capitalism or whatever you call it. The other side, there's a need, there's a demand, and the supply. Supply was not there, demand was there. So by then, the world was actually having a lot of population also, because humans could survive, and they were able to cope with the hardships of the nature. And so population kind of, it was not in check. So people needed more things to be produced. And so the concept of industrial revolution, where large factories using mechanized equipment, and using a kind of a giant energy, not just horses, but many 1,000 horsepowers they wanted to have. They soon, with the steam engine, they were able to have a prime mover which will move everything, right? That same thing, it transformed to the fossil fuel and the electrical energy, and what we see today. So this is one of the early photographs. Probably Bombay used to look like this, with a lot of mills, and you can just imagine it would be very dirty, polluted. So the pollution started, the carbon footprint, so-called, warming the globe. This looks like a cattle shed. This is the first production line of Ford, Henry Ford. One side, the chassis will enter, the other side will leave with four wheels. Each one adds something. So division of labor was born, production line was born. And well, today also it remains very much like this, only with a lot of sophistication, less people, more robots have come. And so we are heading towards Industry 4.0. In fact, with the advent of electromechanical devices, the valve radio, valves, transistors actually brought the miniaturization, and later on, there's no looking back. The computation started taking shape. NCs became CNCs, normal machines became NCs became CNCs, and automation started. And so we call that as industry uh, 3.0. We'll see that later on. So the modern name of art of making things was given by engineering discipline as production technology. So if we look at production technology, predominantly there are three areas by which we can produce anything in this world. One is subtractive way, additive way, and formative way. Why I want to stress here is, as a practitioner, I want to tell you some truth. Okay, many times we call 3D printing as additive. Why it is additive? And additive manufacturing also we say. So I would like to a little bit bust myths on this, by showing you this. So if you look at the manufacturing process, we have something called as a plus process. We have something called zero or forming process, and something called as minus or subtractive process. What is this plus additive processes? They are casting, welding, cladding, painting, plating, gluing, lamination, coating, and 3D printing. So I would like to draw your attention to this fact. Under the manufacturing umbrella, which is a larger one, you have plus process, zero process, and minus process. Under plus, the additive processes, we have so many, of which 3D printing is a subset. This is very important. This realization is because I have been practicing this. So people have coined additive manufacturing. But what is manufacturing? Manufacturing means making millions. Okay. But as a practitioner, I don't see 3D printing we use today to make millions. I don't think there is an intention to make millions in future also. Because that is not viable for me. Why should I do it? Probably I will put some 1,000 3D printers and I can make a million. No issue. So in the world, there's so many 3D printers put together. They may produce so many millions, right? But today, in one factory, people produce. Every second, something comes and gets generated. It is ejected out every second. Cycle time. If you look at that, I don't see. Probably one day it may happen because of some disruptive technological things may come. But today, 3D printing is time consuming. Also, it is expensive, and it will take, we don't want to use it to make millions. Okay. I'll come back again, why world doesn't require 1 million in future, so that's one more thing we need to discuss. So coming to zero or forming processes, we have bending, extrusion, drawing, forming, forging, coining, rolling, knurling, embossing. Why it's called as a zero process? Zero process because we neither add something or remove something. So it is like, if I'm rolling something, a plate is going under the roller, the input weight is going to be the output weight. Maybe very small things may be lost. Wire drawing also. If I bend something, the weight will not change. If I'm doing coining or if I'm doing forging, all these things are, so we call it a zero process. Now coming to the latest or conventional manufacturing, we have been very familiar with minus or subtractive processes. What are they? The turning, shaping, milling, drilling, planing, broaching, trepanning, sawing, reaming, grinding, filing, chipping, all these. Now, I don't find the world can get rid of these three processes, the plus, minus, and zero. Why? Because each one have their own merits, and it is very important, just like what we say in operation research, some amount of X and some amount of Y I need to do to maximize my profit or minimize my time. That's what we talk about all the time. That means I need to use certain amount of additive certain amount of zero, certain amount of subtractive in order to be viable and most effective and most optimal. Okay, we can take it as a hypothesis. We can later on prove, but I want to bring to your notice that please understand 3D printing is a part of additive processes, umbrella, term, and also additive manufacturing is something which is potential is there, but today it is more, I would like to call it as digital fabrication. I think your principal referred it, the term digital fabrication. That's a very good term. As a practitioner, I would like to recommend this process of digital fabrication. I can make one. Making one is not a manufacturing, It is a crafting or it is a fabrication. So you call it as a digital fabrication, digital crafting, digital whatever. When we say even digital manufacturing, the term would be a little different. As a matter of fact, the term manufacturing was invented during the Industrial Revolution because of the capability to produce a very large volume of material and interchangeably which can be used, and the landed cost was very low. Well, so products, what we use, what we have been using, what we'll be using in future are all conceptualized first. Somebody thought about it, addressing a problem, and this is an iterative process, and we call that as a design. Why? Because whatever you do first is more like a initial thought which was there in your head, and it's taken out on a piece of paper. And when you have it on the piece of paper, you have a dialogue with that sketch, or you externalize it and show it to others, and they also add to it. And so goes the synthesis. Synthesis is like cooking, So you're cooking something, namak zyada ho gaya, kam ho gaya, you start adding and subtracting and to make it good, good for taste, right? Taste for yourself and taste for others. So iterative, because you don't get the good result in first go, because you're going to improve upon it. And this improving as a design process is universal. Whatever you designed yesterday is not relevant today, and tomorrow again whatever you designed today is not relevant. So design is something which is continuously changing. Design is something which is continuously changing. That's why we say iterative process. And people today have different tastes. You have different products. You have a phone, different varieties of phone. You have anything, you take anything. You have cars, variety of cars. You take any small things also. A variety is there. Why? Because people want to improve all the time, and world has been doing that, in order to bring the products, and they kind of iterate, try out many things. If you want to make one artifact, you try to conceptualize in many ways and see how good it is, evaluate, validate design. And this has been done not just by sketching something, but actually physically making it, and that needed a lot of skill. And this is done by a very system approach, having a kind of a systematic technique called NPD. NPD means a new product design, and industry follows this world over. These are the days when design thinking was not yet born. Okay, we call it as design thinking today, But when I studied design, it was not called as design thinking. It was called as designing or design methodology. And so going back to this, you have a lot of problems and or opportunities or gaps, you want to address it, and so you do synthesis. You start cooking. What you start cooking ideas, and these ideas, I also have a target. This target market, they cannot give more money. They cannot be, it has to be low cost, for example. So ideas are generated many, and they are screened, filtered off. Like, for example, cost is a filter, or it could be manufacturing capability or feasibility is another screen. Likewise, they have criterias. If they fulfill, then they further go down to detailing. That is called design. What is detailing? Detailing is nothing but the embodiment design. That is nuts and bolts. What material, what thickness, who will do it, where they do it, 5W1H, all that will come in the detailing, the planning and thereof to make in large numbers. And no design can be ever accepted just like that. You cannot build a car and think it will run. You have to check whether it runs or not. So testing becomes a very important thing. And how do you test it? Test it by actually making working prototypes. So making prototype became a kind of a very important thing before you can launch a product. And people have been also trying to check why one need to do prototyping. That's because the cost committed curve to the cost incurred curve are little opposite or inverse. While you are doing concept design, it doesn't cost you much. Either be up canteen mein jaake you take a paper napkin and start drawing something, that becomes a concept design. Correct. Then you go back to your lab, or you have your laptop and you start putting it on a CAD. Then it becomes a detailed design. But the moment you say you want to make it, the cost is zooming, right? So world over, people are trying to check the idea whether it is good or not by a kind of validation is always done, without which they don't go further. Otherwise, they lose a lot of money, right? So you can do concept design, any number of concept designs. You can also detail if you have time, but making you need to be very careful. So you can have 20% cost, you could contain that. 80% you can save. So how this is done? People take any idea, they want to make a small prototype, they check it whether it works or not. That gives them kind of it de-risks businesses. So I can call this as a business case. Business case why people want to go for making a prototype. And in fact, in the various stages of product development, like planning, concept development, system level design, detailed design, testing and refinement, and ramp up, you have a role of prototypes being played here. And I want to draw your attention to particularly to testing and refinement. There are 3 stars here. That shows we have a higher emphasis of requirement of a prototype in the testing and refinement area. Why? So, as we learned in the morning, we should all create novel things and we should protect IP and all that. But in a large country like India, with so many cases pending in the courts, having an IP and trying to protect it is very difficult. So, what companies are doing? The companies want to create number of versions. So copyright is right to copy. We say, well, in a lighter way, ironically, that copyright is right to copy. So the moment you bring a new idea into the market, It is not the customer who will see it or customer will care. He wants to use it. But the competition, the competitors, they are the ones who want to have a look at what you have launched. And if you have a problem, they can improve upon it and they can relaunch it. And they'll become success and you'll become failure. So what companies are trying to do, nobody can actually stop this copying. In some way or the other, people circumvent and they copy again. So what companies all over the world are doing, they want to develop an idea and they keep on improving it. Make a version 1, version 2, version 3, version 10. They first launch version 1. Somebody starts copying it and they will launch this version 2 because they already have it. So the company, there is no competition for them. They compete with themselves. And the companies who are copying, they are infinitely copying only. They are unable to launch anything because the market is saying new versions. See the race of you have iPhones or smartphone from Samsung. So much competition, right? And people still don't know what to expect, but they will know something new will come every time. Correct, no? And so what is that driving? So the companies in their own idea kitchen, R&D, they will do testing and refinement. And that becomes a big business case. It will de-risk, not only of project failure, a product failure in the market, but also ensures you have a leadership, by competing with yourself. And that's why people are trying to do the prototyping. Now, what is the connection? So historically, 3D printing was called as prototyping. Why? It has got a context why it was called so. Because of the requirement of prototype, one needs a lot of skill. That skill was not available all the time. So when it is not available, what will happen to the cycle? The cycle will get a kind of a bottleneck. Planning is done, concept development is done, system level design is done, detailed design is done, but I need to test now, but there is no model available, working model available to test. So that used to be a problem, bottleneck in the time to market. So people used to make prototypes, simulate prototypes or designs using various alternate material, clay, puff, cardboard, electronics, or circuitry. They used to do it on a breadboard like this, or they will arrange a manifold by which they will evaluate many things, usability, things like that, look and feel, and the ergonomics and all that. But this has to be made and assessed, evaluated. So this needs skill. The person who does all the conceptualization may not be skilled to do all this. So you need a different class of people who are skilled in carpentry or model making, pattern making, And there was a trade, I remember, ITI, pattern maker was there. But today it is not there. They're not found anywhere. So the world was suffering actually from this. And this was one of the trigger. With the advent of, the computation, people had some kind of a relaxation. They said, everything I can do it on computer. Prototyping, okay, I do it on computer. I want to test them a thing, okay, I will do it on computer. I want to check the flow, I can do it on computer. Now, whether this mechanism works or not, whether it meshes, I can do it on computer. So the computing has given us a lot of power, starting from creating a virtual object to including the line, factory line, where you can check and simulate the production, the so-called time motion analysis, the so-called optimization of layout, whether a process layout or a product layout, all that people can do now using softwares on computer. But will this, if you go to the management and say, I've done all this product perfectly works, now you fund me, they will not fund. They will not fund because they may not understand all this. They want to see a working prototype. At the end of the day, the product has to work. So many times making a real high fidelity prototype became a absolute need to go ahead with the production or putting a production line. And so this was a great bottleneck in the world. And so this particular thing, time to market uh, became a problem. In order to, without working prototype, it is not possible to go. And making high fidelity working prototype was a real bottleneck. And this is what the so-called the early on 3D printing, or whatever it was called as a rapid prototyping, was born. Dr. Kodama and others, they started looking at it. What was their sole aim? I have already a computer model, and how can I produce directly some part quickly so that I can validate the idea and go ahead and do the next stages. So the trigger in the early development of this technology was time to market, the bottleneck found in the NPD process. Okay, and that's what motivated many people like Chuck Hull also to work on it, and they were able to succeed actually. And that is the trigger why and how this technology came into being. Very important. So digitization of manufacturing has been happening. We all know about it, and in fact, you have so many things happening. In the last 10 to 20 years, the world has changed a lot. In the early millennium, you had Y2K problem that gave a great boost to IT industry. So look at this. The Industrial Revolution 1, 2, 3. So at the ending, you see 3D printing is born. 86. Okay. Now we are at the cusp of Industry 4.0, wherein we are now looking at a totally automated, augmented, and remotely controllable new regime of manufacturing, and wherein there is no need for human beings to even get in. Human beings are mostly replaced by the sensors. There are cameras and they are connected to AI. They can recognize, they can trigger so many things. They can take action also. So we'll not go deep into that, some other time, but not in the scope of today's talk, of course. And so now let us rewind. World, since the Industrial Revolution, has been taking a lot of tons of material, removing material, wasteful material. The chips, what you say here, you cannot even eat. Fully, I mean, it's totally wasteful. But still, even today, world is working depending on this. Even today, this is the lion's share of the production is done through subtractive manufacturing. And this deficiency was kind of addressed by a new way of making things. And why? Yeah, you have any doubt here? Hello? I think we are now moving towards a new way of making things, that is directly from CAD to part. A transformation that is happening from a virtual entity to a physical entity. And here I would like to connect you the Industry 4.0. They say cyber physical systems. The cyber physical systems, physical side is brought by 3D printing. not only by 3D printing, but all by the additive, subtractive, and zero processes. These are the things which will be going into making of anything in future. And how it is done? By CNCs, the 3D printers, and of course robots. All the three will be a kind of a holy trinity that comes together to make it. And it is a regime of art to part transformation. So if you can conceptualize and have a doodle, you can do the 3D content, virtual entity, then you can digitally render it, and you can actually physically build it, fabricate it, right? So it's truly a regime wherein we are actually able to get this capability of translating art to part. And how it is done? It is done through a series of processes, which we call as the workflow. The virtual model is actually made on a computer, exported, and it is sliced by a software. And these slices are put back layer upon layer, and it is done by a robot. Yes, it is a robot. A robot is called as 3D printer. Okay. And in the early days, it was called as rapid prototyping. Now we call it as 3D printing and maybe even additive manufacturing, but with a pinch of salt, because it is not. So virtual model, triangulated model, and all that. So many file formats and slicing, just to conclude. And it is putting so truly the integration of things are happening. In the mathematics, we say integrate with a big elongated S, but actually this is the integration of those layers, truly, which is physically seen. What is 3D printing? It is integration of layers, which is sliced of a virtual entity of the part, which is intended, to be produced. And so, well, in fact, people started looking at it. In fact, there is one more which will get added next talk. DED is also there now. SLA, SLS, FDM, LOM, binder. So 3D printing means what? 3D, for some it is SLA, some it is SLS, some FDM. But actually it is all same. It's all 3D printing. So 3D printing is a set of technologies. This is how I define it. This is my definition. Industry definition. 3D printing refers to a set of technologies which will help to fabricate 3D objects layer upon layer from digital input data. The inputs could be from 3D model, medical image slice data, or point cloud, right? Very simple, very, very pictographic. You cannot forget it. But the beauty of this additive, we'll accept. World is calling it additive. Let us also call it as additive now, for the time being. But I still would like to call it as digital fabrication. Okay, and you can see a lot of chip is produced and a lot of wasteful energy in the conventional processes. In the new process, the scrap is less and also energy requirement is less. So what it means is we are actually looking at a better option to produce things. Well, will it all transform or disrupt everything? No, I don't say. I don't believe it. Because as a practitioner of this technology, I've seen in the last 35 years, the growth has been largely of a evolution than a revolution. And because it is not a revolution, it is not right now disruptive. And for a long time, it has to play a complementary role with the conventional manufacturing. Very important. I'm making a very profound remark here because, and that's where we would like to park the thoughts. And the beauty of just-in-time, the U layout, the quick change of, somebody coined that word, what is it called? Just-in-time, and what is it called as quick change of, single-minute exchange of dies and all that. But today, if you look at this, the same equipment is capable of doing many things without any setting, without any, fixture, without any jig, and only driven by the CAD. It is able to do so many shifts, right? And without any tool. So sometimes we call it as a toolless manufacturing. Toolless manufacturing. So it is also going to come under generative. So how in lathe we can turn is also a kind of a generation of a form. A 3D printer also can be called as a generator of a form. That's how we produce it, right? And moving forward, we have these pioneers. Dr. Kodama, though he could not get a patent, he had filed a provisional patent and he could not fund his final patent. So pity. Otherwise, he is the guy who actually discovered stereolithography. Much later, people can always think same way. I don't say Chakal copied, but it is a state of art. When you have a UV light impinging on a photopolymer, you can expect the hardening of the ground, solid ground curing and all the earlier terms which are still used in the many technologies. So it was Chekal who actually got the patent. Closely behind him was called Decoid, who used Chekal used a liquid photopolymer, Coral used powder, nylon powder. And even very funny is Stephen Scott Cram. He had a trigger which was not like Dr. Kodapa or Chekal or Coral. He is a common man. He was a father of a small little girl who had a broken toy, and he thought, what if I could have made something which will just work on this broken side and complete it? And this brilliant, commoner, he started working on it, and he and his wife, they start this company, Stratasys. Even today, FDM is one of the simplest of all the technologies, and it became open source. And so I'm sure all of us keep using FDM a lot. And in fact, the early mission was looking like this. The first part made was looking like this. Even today, Chuck Hull, Charles Hull, is the emeritus CTO of 3D systems. And he coined a very beautiful term, which was probably never there before. It is stereolithography. Stereo means depth, lithography means printing. And he had indirectly called it as 3D printing. And you can see this is the commercially available SLA system. Many people wonder what is SLA here. Stereolithography is SL. So we can call it SL also, SL technology also. Sometimes people say SL technology, or sometimes they say SLA. A stands for apparatus. Okay. So many people don't know. SLA means A is apparatus, because it was considered to be a lab equipment, to do something. They never had vision to call it as a production system, right? But it became one. And that's the kind of disruption it has brought in some sense. So ASME or ASTME and all, they formed a group to segregate these, and they call it as VAT photopolymerization or photopolymerization, just like that. And you can see through this small animation, you're able to see the operation of this. Hello?
Hello,
Is
Mr.
it boring you all?
Ashutosh.
You need a
No,
break?
not at all.
You need a break?
Mr. Ashutosh, please. No, sir, we can continue. Mr. Ashutosh, please mute your mic. Mr. Ashutosh. Mr. Ashutosh. Mr. Ashutosh. Kashmiri, you can mute this. Kashmiri. MIS manager Kashmiri. Mr. Ashutosh, please mute your mic.
This is something like students doing with us.
मला बी लिहून दे होती लिहून घेऊ दे रे बाबा जगू मला बी लिहून घेऊ दे.
The host
Ashutosh,
can
Mr.
actually.
Yeah, host, I'm connecting with host. Let me just give a minute, sir.
देश पांडे नाही संध्याकाळी हो आता नाही संध्याकाळी गेले ना फक्त सिक्युरिटी गार्डला देऊन टाका. आपण काय करू उद्या नाहीतर ती बाई रात्रभर दिमाग खाईल आपलं.
Sir, administrator has the right to mute any participant, so I would request administrator if they can mute.
I think it has subsided. I'll start. Let us. And you can see this liquid when you're ejecting it from the table. It looks like this. These are crystallized. The photo polymerization from a monomer liquid. It transforms to a cross-linked monomer becomes a polymer, right? And so beautiful. And next technology is powder bed fusion, and the inventor called it as selective laser sintering, SLS. Okay, and it's quite popular and most dear to me because you can create something impossible using this. Let us see how it looks when we do the animation. So there is a powder and there is a rolling pin that will spread the powder on either side, to and fro, right and left, and subsequently the layers are all sintered, and the sintered layer goes down. Okay, let us take a closer look of that. The powder particles are bound together, at the contact point. They get a kind of a taco welded, and because of CO2 laser with a Gaussian distribution of power, it not only stitches the top layer, but also it will stitch to the bottom layer. Okay, and thereby making a very sound object. And you can see it could be a little bit porous here. This happens with nylon, and when you work with metal also it can happen. So when you increase the power of laser, you're going to use a fiber laser there. It is going to have a melt pool, that we'll see in metal. Okay, and so this is how a CO2 laser will bind the layers to make the object. So you can see here on the left hand side you have a concentric circles getting formed. So that is sintering. The laser is binding the powder, and the powder becomes a kind of sheet like thing there. And because there is one more layer of powder coming again, rolled and compacted, and laser is again acting on the same place, the whole thing becomes a concentric cylinder or a tubing or whatever section. At this section it is looking like this, but it can keep changing. And then you kind of eject the whole thing and extricate these things like excavation of archaeology. The parts are hidden inside. You uncover them, removing the loose powder off, and by this we can actually create objects that are what I can say. I'm sorry. Objects which are interlinked or assembled, or which are nested also, one inside the other, can be done because you can shake the powder to remove, and powder here acts like a support, and we can play around with the tolerances of two parts which are moving, having a relative motion that can be brought about, because in CAD there is no gravity. You can play, we can keep anything suspended. You can take a sphere and put another sphere inside, another sphere inside in a CAD, because In CAD, they stay. It is like there is no gravity in CAD. When it comes to 3D printed also, it will behave as though there is a zero gravity because powder is supporting it, all the planes. And when you remove it, when the powder falls off, then only the effect of gravity starts, acting on it, and they fall one inside the other. So people will be wondering how this went inside, or how this link happened. Now, how anybody went and assembled it? It's because you have already done it in the CAD itself. It's an assembly which is going inside, and for this car, for example, or a Jeep, the wheels move because there is a relative motion that has been maintained. And when you are exporting it, you don't necessarily take it down, but they are concentric, like a floating. And once it is getting printed, the same thing, the powder in between will fall off, thereby you're going to achieve. Hope I got it. And so the next technology is FDM, the fused deposition modeling. Some people call it as a free-form fabrication also. And the Stratasys, the company, on the right-hand top, you have that system. You have a low-cost one in the foreground, and it's a printer, a Chinese-made printer, and each of them have a huge difference in price. But what they produce is same quality. Only difference is in the top one can expect this to work 24/7, 365 days, and you want it to print, it will always print. So what we are talking about is reliability of system. Okay. Whereas the one in the foreground, the red model, what you have, probably it may work today, it may not work tomorrow. I mean, you have to make it work, So reliability is the issue, but if they produce the same kind of material. That means here, probably the company did not sufficiently innovate, the Stratasys people. It became open source, and today people have not only taken it out and improved upon it. That is the beauty of it. So what you see here is a MakerBot. In fact, MakerBot was the first open source commercial machine which came outside Stratasys. Later on, Stratasys kind of bought it over. It was like killing the competition there. And of course, we have another technology called LOM, is laminated object manufacturing. A company called Halisys used to do it with a laser, what you see here on the left-hand side. But they could not actually make enough money. It became bankrupt. And on the right-hand side, you have MCOR. This is an airline company which started using a kind of blade to cut a paper. And they were also promoting as a biodegradable one because it uses paper and all that. Somehow they could not actually sell well because industry cannot adopt it. It is not a durable material, and the glue is again making it not recyclable. So whatever promise they did, though it can make a very juicy orange, what you see in the bottom left-hand side, right-hand side, this can be made as a model, but it has no other application other than display model. So it can be used in medicine, it can be used in teaching purpose, toy making, etc. But it doesn't have an industrial application as such. Okay, and that's why this company, MCOR, also got shut down, and there is a new company which has come, again with the same new avatar. Then comes the MIT work. MIT America, they were also looking at this, how to make this technology. They were very close to the analogous selective laser sintering, that is SLS process, what they developed in Texas University. Here, they developed something. They were not using a laser to sinter. There was no sintering here. In fact, it's a cold process almost. So they had gypsum powder and they spread some gum adhesive, and the adhesive after touching the powder kind of absorbs powder and becomes a hard mass. And if you can spread one more layer, again I am going to stencil some kind of glue. You say print head. The print head will print glue, not ink. And when you print the glue, you spread the powder. The glue will absorb, and that this thing is kind of sintered. So sintering per se by laser is not required here. So beautiful, no? So it's called as binder jetting. Binder means binder is adhesive, adhesive. Because of adhesive, it is going to become a solid. So it is not polymerization, it is not sintering here, but adhesive action. And this particular thing they called as 3D printing. So much so they are trademarked. So MIT technology was first to be called as 3D printing. Okay. For a long time they were sticking to that trademark, but later on when world started calling everything as 3D printing, they somehow gave up their rights. And so even today, we call it as 3D printing, thanks to the term actually coined by MIT, and it was for binder jetting. You should know historically. And you can see here a demo of how this wonderful technology works. The powder is first spread. So when I spread the powder, it is like a paper only. On paper, you can have a plotting or anything. And if you do the plotting, and you normally think of only 2D. Here, because it is going down every time, you can see the whole building comes out. When you vacuum the powder off, you'll be able to see the building emerging out, like a magic. So this same thing happens in SLS also, only with the difference, this is binder jetting, that is selective laser sintering. There the action is by laser, here the action is by binder. Binder means glue, adhesive, right? We can try this, in your colleges, you can try this. You take a ATA or anything like that, you put some glue, take a stencil and screen print a glue, take it out, again spread one more layer of ATA. Again you put glue. So you'll be getting same thing. In fact, selective laser sintering was also done same way, putting powder by hand on all that, very funny. And that's what coil decoy did, and probably that's what they did in metal also. Much later they have all mechanized it. Now it has become a machine with all the things. Yet another wonderful technology is metal jetting, wherein you're for the first time able to create a kind of a functionally graded material. That means I have component A and component B. I can mix them in varying proportions, and I can the end result is either I can have more of A and less of B, or more of B or less of A, or equal A and equal B. So I can play with things like in a same component, one side transparency, another opacity, one side hardness, another side softness. One can achieve, that kind of So they call it as a digital material. Why it's called as a digital material? Because I'm able to by computing and programming, I can specify what is the hardness, what is the transparency I need for that particular small 3D pixel. 3D pixel is called as a voxel. In that particular small cuboid, what property I want to assign, I can actually program it. And so, and this is also dispensed by automation. And so we call it as a digital, because it is all controlled by zeros and one of computer programming. The term digital material was born. And this company, Object, was a Israeli company, later on taken over by Stratasys. Today they're part of the Stratasys team, and it's a wonderful technology. Somehow, uh, still they need to work on it. It is not, though it's very good, very expensive, and in fact, if I were to tell, tick which is the most developed, best 3D printing, I will say this one, metal jetting. Why? Because I can make a part, all at one place. I don't have to have a o-ring. You can see o-ring, soft o-ring, and the half white manifold on the actuator, which is soft to touch but hard inside. That kind of material, it's a composite. In a way, it's a composite material, which is because of the uh, various permutation combinations of the mixing of A and B, or maybe C, is possible at the click of button, by programming. uh, I think this is the best one can look at 3D printing as. In fact, human body, we are all produced with in the mother's womb like this. We have a hurdy which is very hard, and, we have soft muscles and all. We have bionic eyes, CPU, brain, all that. And nature is nothing to, nature is the best designer. Again, a connection from the term design. Nature is the best designer. Whatever we are trying to imitate, mimic, is in a way looking at nature. So people, same thing they follow to bioplow printing also. They say we can print organs the same way. They're simulating. You fake it before you make it, kind of thing. And you can see in material jetting, actually the consistency is like a paste, toothpaste. So they put it on the substratum, and it is exposed to UV light. So it's a photosensitive paste, a photopolymer paste, I can say. And so it is material jetting here, not binder jetting, material jetting, because material is getting deposited and UV light exposure makes it set. So it locks it. There is no further reaction that can happen. And so that's, then we have, of course, the directed energy deposition is another major technology. In fact, a class of technologies go under this. Electron beam melting also. Electron beam melting, sometimes we classify under powder bed fusion also. So a lot of things, SLM, you have UOS having the DMLS, they're all one and the same, different semantics, that's all, in a way. And people are nowadays, they're even trying to use feedstock as wire, metal wire. And the metal wire technologies are going to really disrupt compared to the powder-based ones. And you can see in the metal how the whole thing, the powder gets molten, and this molten metal means the specific gravity is higher than the powder. The whole thing sinks. So in metal, supports are very important. They are absolute must. There are exceptions there, but because of which it also complicates polymer printing to 3D print, metal 3D printing. You can see here DMLS, how metal is getting sintered with a fiber laser, and the sintered areas have become a sheet of metal. They're all surrounded by powder, and this powder is not capable of supporting like in SLS, because the melt pool is heavier than the powder specific gravity. It will start sinking, or it will start shifting, and the temperature, as and when it gets deposited more and more, the heat capacity also increases. So the thermodynamics of it, heat and mass transfer of it, and the stability, so many things, and the mechanical heat affected zone, and this heat have to be taken out quickly. So heat scavenging, what we call, this is all going to be very important, when we move. And so people have tried to use powder or wire, to take it to a tip with a laser beam. And when the powder come, the whole thing melts, and you put a drop, on the subplatter. It's called drop on demand kind of thing. So using many drops, you're able to actually make the whole entity apart. So this is very interesting because this can convert any CNC into a metal 3D additive. I will show you some, maybe two more next stop. I'll go a little deeper. These are some of the metal printers we have. And look at this. So far, we have been looking at all these boxes. They're all boxed. So far, we have been seeing boxes. Now, you see something which is out of the box. This is a KUKA robot, which is a general purpose robot, which can be programmed in multiple ways. And what people have done, they have put a kind of big syringe, and they have a magazine feed of clay, a red clay, and it is getting deposited. And the data is actually read from a computer. So question is, can we call it as a 3D printer? Yes, this is a 3D printer because it can create entity, and it is building layer upon layer, and it is getting the whole input from a digital data. In fact, it is out of the box 3D printing. It can print not only in that station, but all around it. It can, so if you are thinking of a food printer, so it can make something, food, and that becomes ready, and the next, it can go to the next station, then the next station, like that, all around it can move. So I think the robots have the highest dexterity, and we can say a lot of future 3D printers will be based on robots. And look at this is a 3D doodler. So my question to all of you, whether we can call it as a FDM printer, you can unmute and answer this question. Can we call it as a FDM printer?
Yes, sir.
So how many of you say yes, along with your...
Yes, sir. Yes, sir.
Well, no, it cannot be called as a 3D printer because there is no digital input data. Okay. It behaves as though it is a FDM printer. It is like a glue gun. It is like mehendi lagate, I say. And it is no doubt depositing. Layer by layer, forget it. It need not be always layer by layer. But digital input data should be there. If it is not there, then you can say it is not 3D printing. Got my point? So the hands are there, and you've got a thinking in the brain, and it comes, and you're forming something. That cannot be called as a 3D printing. So you can see how it is being done. But what happens if this hand is replaced by a robot? Can we call it as a 3D printer? What if I replace this, the hand by a robotic actuator? Then we can call it as a 3D printer. It becomes like a same thing as your KUKA. So let us see one example. See this one. This is, in fact, depositing not even on ground, against gravity. It is depositing something on a side wall. And believe me, even this can be called a 3D printer because it is getting a digital input data. It can make one, it can make 100, it doesn't get tired, and you can check the consistency also. It is going to be same. So you can see how robotics are actually changing the way we look at 3D printers. In fact, it is additive, but not printing many things in this world. Moti hai, moti is additively made. Onion hai, onion is additively made. You have so many things like that. Wood, you cut a wood, big tree. You have annual rings there. Why? Because the growth is increasing every day, every year by organic means of material deposition, right? And so this is additive, not 3D printing. So it's very important when you're going to take on creative students. It's important to understand this. Somebody may say, hey, this is additive, but it is not 3D printing. What is the example you can give? Laddu is there. Very interestingly, this also additive, but not 3D printing. I want all of you to understand one thing here. Very, very important. There are so many slides, here, very much similar to a 3D printing. And at every layer, it is made up of so many layers. At every layer, I can put chutney, or I can put cheese, I can put jam, I can put ham, I can put, anything there, vegetables and all. So it changes. So, for example, if you take a casting, I cannot do the casting like this. To some extent, sintering you can do. But even sintering is difficult because after you have powder, you compact and you sinter it. That's it. You don't have to, not necessarily you can change the layers. But in 3D printing, I have a control over every layer. At every layer, I know what I can deposit. Isn't it? That is very important. By this, what we can learn is in 3D printing, we have a capability to control what you deposit every layer. Depending on that treatment, what you gave, it will change the property. For example, laser exposure also, power also, I vary. I can create different material property. And that is the beauty of additive manufacturing, which is not there in forging, it is not there in injection molding, it is not there in die casting, it is definitely not there in CNC. That is the greatest advantage we have with additive manufacturing. We are able to control properties at a layer. And I told you, digital material, you can even control the property at a voxel level. Voxel is a 2D, 3D pixel. And in fact, it is Adrian Boyer and his team, and they started, demoting this concept of parent and child. 3D printer printing itself. So the cartoons like this appeared. In fact, yesterday in Facebook, I saw something I want to show you. So manufacturer files for bankruptcy. Why? 3D printing company asked client not to print 3D printers. So if you are selling a product, using that product, you are going to create the same product again. Like what we saw here, the same thing we are able to see somebody has done. This is a Mojo printer. Some of you must be knowing Mojo printers. And so these are fun. I mean, it's not happening, but it may happen one day. In fact, we have a technology called multi-jet fusion, MJF. There, 50% of the parts are printed by the same machine. Can you believe it? More than 50%. So many rollers, gears, stoppers, many things are made. 50%, of the parts are from the same printer, printed on a similar technology. I can say, if not same. So today we have these consumer printers, which are coming in all shapes and sizes, and the whole technology, once it got adapted, it's good, making deep inroads into various um, domains in manufacturing. It could be, aerospace, automotive, dental, electronics, jewelry, medical, FMCG packaging, lifestyle, architecture, automotive, aerospace, white goods, electronics, electrical, plastics, and many more, gifting also, customization. It goes on and on. Food, you have cloth, you have what you cannot print is the question. So what you cannot print is a question. So what are these? These are truly unimaginable products and also impossible to make products. Okay, but they're all possible today. Now, thanks to this technology. Now, at this point, I would like to stress upon the beauty as a industry person. What I say is 3D printing is used mainly for these 6 reasons. There could be many, but I consider them to be my top list. One is part consolidation. That means I can have any bill of material that can be squeezed to one item. So that's the capability. So you can make about 31 to 1, 50 to 1, 300 to 1, like that kind of zipping one can do. Part consolidation. Part consolidation brings a lot of reliability to system because the variabilities are reduced here. And injection fixtures also, we can quickly make something on demand. That's why it is being used. Lightweighting is something which is very, very important. It is required for airborne systems such as rocketry, um, uh, satellites, and the so-called aeroplanes also. And why not drones also, for example. Drones people are using, where payload is optimized by reducing the total, dead weight of the equipment. That is done by lightweighting. So the strategy is to go for organic forms, and these forms can only be printed. They cannot be done by any other way. Coming to complexity wise, jewelry is one of the most complex when it comes to manufacturing. So people are looking at it, and it has disrupted the jewelry making to a large extent today. In the world, anything can be made small or big at a click of button. Right and left we can do by flipping, at a flip, a split second. And so complexity is very high in jewelry, and for additive manufacturing or 3D printing, complexity is fine. Because it can handle at no extra cost. And world is also looking at one-off products, need for one part. Whenever you make anything one part, you cannot be always viable. But how can you be viable? Conventionally, it's difficult. But from additive manufacturing or 3D printing area, if we look at it, it is definitely possible to make one and be viable, affordable, and so it's very important. We do a lot of customized things where you require just one. For example, prototype also. Prototype people will not make many. They take just one and they want to check it. And mass customization. Customization is something which is very high in patient-specific solutions in medical, and so while it can act in any sector, medical sector stands to benefit most when you do customization for a particular patient. And we cannot call it as fabrication. No, we can call it as fabrication. We cannot call it as manufacturing because you're not making millions. You're just making one or two of what is required. That's it. So people have tried to print something big. People have tried to print something small also. And you can see a nanoscribe can print very small. In the bottom left-hand side, you have 20 micron green line. And that shows the scale, right? So what will be those verticals window on the top, cheja on the window can be. It is definitely micron level, right? So people have tried to print big and they're also trying to print small. And what about this? The foreground, you have a printer, and the background, you have a memo. How they have printed this? Well, by digitally cutting it and making into small blocks, they can put them together to get the whole part. Okay. That's how they have built it. So this is one of the greatest virtues. Many times you can digitally cut apart and glue it. Now you have Loctite and other stuff which are very good glues. So the industrial scale 3D printing will look like this: shop floor clean and cool, no dust, no oil. This is the future factory in a way. This we have been emphasizing, like your faculties in the morning also described this. There is complexity will come for free, and there is no economy of scale, because you make one number, 10 numbers, 100 numbers, 1,000 numbers, 1 million. The rate for one part will not change so much, because it is a layer by layer deposition, right? It has to make so many layers, only then get ready for the. So it is very important. We cannot compare it with conventional manufacturing, subtractive manufacturing, when it comes to bulk production. But complexity wise, in conventional, more and more process go on, more and more you touch, you actually lose value. So people say complexity comes for free, is not really always true, but in a way it is tapering off slightly. So where do we actually see this technology in the manufacturing world? So you can see the volume game is even today is done by only subtractive manufacturing or other forms of conventional ones, injection molding, die casting, or vacuum casting, like that. In the middle, you have a CNC, which is going to make few batch quantities, and 3D printing is at a very, very different place altogether. Low numbers, but highest complexity. That's where it will be viable. So in the earlier days, when the Czech Hull started looking at this technology, at the center of the whole thing was the hardware. Of course, there is a little bit of the small piece of software to slice and conversion of the model to a triangulated model, STL, and material, some few materials. That's it. So the opportunity was more in terms of hardware, software, and material. They were just complementing each other. That's all. But soon, today, it has changed. Hardware, software, and material, they have a lot to have overlapping. And in future, the hardware will become mostly saturated, and the hardware, once you say it's saturated, a lot of me too kind of objects will keep arriving. Like you have today Apple phone and Samsung phone, plus minus they are very similar. Saturation, though they're trying to push the boundaries, make it novel every year, every time. Somewhere, at some point, a screwdriver is not studied in mechanical engineering because it is such a simple thing. So same way, 3D printing will not be emphasized in future. It becomes like a screwdriver. But what is important is software, which is going to de-skill, make this whole thing worthy of child play, is by software de-skilling the whole thing. Material, real world requires real material. So that's where we need to really look at material aspect. And the scope, I can say, in future, the research scope is largely in terms of software, in terms of material. So design for X is something which is very important. I believe you have a session by Professor Ravi Kumar. would be touching upon design for additive manufacturing. And so we'll not go deep into it. But these are all part of the earlier paradigms, of what people coined to cover up the deficiencies of the process. DFX, design for X was born, and today, see, in 200 years of conventional manufacturing, and we have to manage many of these, having some kind of a tactful way to do it. DFMA, DFA, DFM were kind of offshoots which gave some kind of a grammar to whole thing. But it is highly constraining on the part of the engineers to be creative. There is no creativity here much left. So they have tried to see different ways of how to address this. Design for manufacturing, design for assembly. So people have come up with parts, and then to throw it, he coined a software, DFMA, design for manufacturing and assembly. And even today, the world is deriving whatever he said for its efficacy. People have been using this, and see how using it one can optimize. So it's a kind of a part consolidation of a different kind. So additive manufacturing was born in 86. So it's a new way of making things, and it has taken 35 years. Very important. So for 35 years, it was called as rapid prototyping, 3D printing, additive manufacturing, and today we are calling it digital fabrication. And I would like to always love to call it as digital fabrication. So if you look at the trajectory where we started, the emphasis of RP was to make mock-up model, dirty model, okay, and the 3D printed model in nylon is a design validation model. Why we say design validation model? Because you put it on a vehicle, you run it for 3 months, and you study what happened to this piece. If piece is broken, then you are very happy. If it is not broken, then also you are happy. Why? Because if it is broken, you are happy because you are able to fail in your own kitchen, and you can go back and strengthen that area. That's very important. And why you are happy if it is not failing? Because after all, it has validated your design. In both the cases, prototypes are being used. Now coming to end user part, AM. The end user part is going to be used in the use context. Means what? It is used in the same way as we do for conventional manufacturing parts, which will have a life cycle of its own. You use it and you retire it, and it will go beyond that. Then you have to take it for recycling. So that means in AM also, people are looking at recycling, but that's a part. This part has the capability to deliver the service in the use context. Use context is very, very important here. And so I can recollect, we had a project with the GE. They wanted to do a SLA model, and we did a SLA model to them. They dipped it in a hot oil, and they're not told, as we normally don't ask anything. So they did not tell what is going to be happening to this part model. They put it in the hot oil, and the whole thing deformed. So every part what you build has to be checked for its use context, and then only it's very important. Otherwise, the 3D printing will fail if you wrongly use it. This particular thing, what you have is a air manifold, And if you do it by a refractory material, high temperature resistant material, nylon, it can be like, it can replace whatever you have now by this. In a way, we are talking about the reliability of the material, the entity what you created, and so it will honor the kind of guarantee, warranty given to this product. Very important. And so end user part is the future. Spectacles, frames, we are doing a lot of medical devices, end user parts, and a lot of things for the COVID time, for the doctors and all, we use it. And so the world is moving, heading towards getting more and more of end user part. It is a prototype, you test it and you can sell it, that kind of thing. So this is what we see. Future is going towards end user parts. Many times in strengthened materials, we assume material to be homogeneous, isotropic. And today, happily, some of these 3D printing processes, they are offering material which are resultant products which are homogeneous and isotropic. I think with this, we come to the end of today's presentation. Hope we started from where, and we ended with a futuristic thoughts on 3D printing. And please do remember, 3D printing is a set of technologies, and 3D printing is something which need to be a strategic tool, in your product design, product development, and your business. And people are looking at it in a very disruptive nature. They're trying to see. But tomorrow or day after, when I'm talking, I'll paint a little different picture of the facts, what industry is doing with these, and then we'll come to know the real, the technology game, why, though it tipped as the biggest revolution or fourth industrial revolution or the next big thing, etc., etc., why it is not able to deliver that promise will be our subject for next whatever time I am going to take. That will be discussed. I enjoyed giving this talk to you continuously. I was a little bit want of water sometime. I can have some water. I'll be happy to stop here and take your questions for a couple of minutes before you can all break for your lunch. And hope we went through a journey of technology. I myself lost in this narration of storytelling, technology storytelling. And we will take some questions. So you may have a lot of doubts. I would like to push it back to the organizers who can moderate the questions. Thank you.
Yes, sir. There is one question in chat box by Kumar Pratyush. The question is, sir, can a design of prototype can be copyrighted?
Well, yes, design can be copyrighted. Not only design can be copyrighted, you can encrypt a file. So I will be talking about those areas in my next talk. Okay, so it is possible, yes. It is not only about copywriting through IP, patent, design registration, etc. You can also lock your file. That's what I meant. You can lock your file. So for that, you don't require STL file. STL file is a dumb file. You should go for something called as AMF and 3MF, VRML, and Leo and things like that, where you are able to authorize the user for one use or many use of metal for plastic, or one you will keep it for 1 year and after 1 year it expires. So it is going to even give you traceability, what file, who is using, where they are using. So blockchain kind of things are also can be incorporated. So all this slowly started building, and that's when I can say the adoption took a hit, and slow and steady it is showing a evolution instead of a revolution. Hope I have answered your question.
Okay, sir. One more question from Natraj Kumar Singaraju. Sir, how many models are available and reliable ones?
Well, you can have any number of models. You mean 3D printers? Is it 3D printer you're asking? So today
Yes,
we have
Natraj, yeah, he said yes.
huh.
In 3D printing.
So 3D printers, you see, they say कुछ पाने के लिए कुछ खोना पड़ते हैं बोलते हैं, कुछ पाने के लिए कुछ. So if you are looking at a very low cost one, you cannot build many things into it. The reliability cannot be built into it. The R&D costs a lot of money. So R&D costs are, again, they want to recover the R&D cost. So when a system is very highly reliable, it becomes imperative that it's going to also cost more, because they want to recover the R&D cost from that, or patent cost or whatever, because they have built such robustness into the system by doing many of it, repeatedly failing and correcting them. So they've incurred some kind of a expenditure, and that expenditure they want to recover. So those reliable systems would be expensive. Okay. So when you say somebody is selling a low cost model, or you want to assemble from internet, you download the files and you get a local market, you bring things and you assemble. Well, it will also work. I'm not saying no. If you have a problem, you come to me, I will help you to make a printer. We can we can help you make a printer, but it may work today, tomorrow it may not work, because it is not built with reliability, and so as and when you start adding things, just like in घर में आपको DP switch नहीं है, तो if there is a surge, entire thing will go. Your computer will go, fridge will go, TV will go. You're going to use a DP switch because that is going to give you risk protection, some kind of a reliability. Suppose I'm giving a talk now, and all of a sudden power goes off. I don't have any problem because I am on a UPS. That means I've added that. So in a reliable system, what they do is they keep on adding layers of security, and that's what makes it reliable. And when you have such a reliable system, it will cost you more. Okay, and so when you ask a question, reliable systems are there? Yes, they are there. Yes, but anything which is very, very cheap, going for a low cost thing, 5,000 rupees, doodle comes for your 2,000 rupees, 1,500 rupees also. And there are printers for 10,000 rupees, 25,000 rupees. As long as you're an expert to run it, you can run it. Because something happens, you have to open and you have to fix it yourself. Nobody is going to give you any kind of guarantee, warranty, anything. It is sold, that's all. Right? Because it cannot have any such built-up costs into it. But a system, what we have, which is very big, they work 24/7, they work 365 days. And if I promise a customer a part, I can deliver it. I'll say tomorrow you come, I'll give you. And this mission will not fail. No crash, nothing. So we have to pay for the reliability. So it's a question of whether we should, what price we are paying for the reliability. Hope I've answered
Yes,
your
sir.
question.
Yes, sir. Yes, sir. I also agree with you. We can see like FDM printer, our students are also like building up in few thousands rupees, and the same FDM type of printer we can see like Status the lowest model maker board comes in some lakhs, like 14 or
Yeah,
15 lakhs.
yeah, yeah,
So that's the reliability. The cost is because it is more reliable.
yeah.
Otherwise, the printers are developed in some thousands rupees also, like the FDM I'm talking about.
That's right.
Yeah. So any more questions from participant? You can mute and you can unmute yourself and ask the question.
Yeah.
Participants, please feel free to ask the question.
Yes, please.
Is any more questions from participants? I think it's okay, sir. So over to you, organizers.
Thank you very much. I love talking to all of you.
Yeah, thank you very
I
much, sir.
can
So
sign
nice
off
Yes,
now.
sir.
insight you have given. A nice insight you have given right from the like old age, what the manufacturing processes and how the history like it evolved, and then the coming to the 3D printing. Again, the different types of the manufacturing processes, plus, minus, and zero, and the various aspects of the 3D printer, like it can fabricate the micron size component to the big size component, and also the complexity that is very important that the 3D printer can deal with. So very important aspect. Over to you, Sadhvi, for the vote of thanks.
Yes, sir. Yes, sir. Thank you so much, sir, for such a wonderful and brainstorming session. It's a great pleasure to propose vote of thanks for this session. I thank you for this valuable time and deep insights that you've shared on the 3D printing and design, present and its future, wherein you spoke about the shift in geopolitical situation during the COVID-19 pandemic, and also told about the evolution of tools and paintings. You also explained the importance of 3D printers and manufacturing and iterative processes, and enlightened the participants by saying that people want to improve all the time, and hence they try to conceptualize in many ways, validate designs, and keep on trying, keep testing with prototypes. Lastly, I would like to say that we are very grateful to you for sharing your immense knowledge and making this session so deeply informative. Yes, sir.
My
Thank you.
pleasure.
Thanks a
Thank
lot.
you.
I also would like to thank all the participants for their wonderful participation,
Thank you.
and I hope to see you all in the next session as well. Thank you so much.
Yeah, thank you, sir, once again. And the next session will begin at 1 o'clock. And at in that session, we are having Professor Y. Ravi, and he will be talking on design for additive manufacturing. The Professor Y. Ravi is from NIT Warangal. And do join this meet 10 minutes ahead of the scheduled time, so that there will be no last minute rush. And please keep your mic on mute whenever the session is in progress, so that will not disturb the speaker. So please keep this in mind. Okay, and you can have the question at the end of the session, or otherwise you can in between. If you have any questions, then you can type in in the type box, and that questions will be taken at appropriate time. So further, the organizing team has given the link for the feedback of the session. You have to give the feedback of each of the session, and in the feedback, you have to type registration number. So registration number you will get from the Excel sheet which is provided in the WhatsApp, or otherwise also provided through on your email. So you can refer to the registration number, and that is mandatory to type in while giving in the feedback. And at the end of the this FDP, also you have to give a feedback to the AI, which is framed by the AICT. So that you have to give from your login after the end of the FDP. Okay. So this is about the instructions. If anything you want to ask, you can ask. Any queries?
So could you please share this attendance link once?
Attendance will monitored automatically, so need not to worry about that.
Okay then, sir. Thanks a lot, sir.
Yeah, attendance also will be shared with you at the end of the day for all these sessions. You can check out your attendance. Okay, so that is automatically captured. Okay.
Right, sir. Sir,
Yeah.
another one question, please.
Yeah.
You said this admission number or some number which is being shared on
Registration
the
number. Yeah, registration number. It is shared in WhatsApp group and also shared yesterday through email. So
Yes, sir.
you can
It
refer
is
to that.
the
Refer to that Excel sheet, and in Excel
yeah.
sheet in front of your name, one column is added about registration number. You can refer to that registration number, and you have to
Done.
submit the registration number while giving the feedback. Okay.
Done, sir. Thanks a lot, sir.
Okay. Thank you. Thank you very much for patience listening, and see you for the next session of today, which is going to start at 1 p.m. Thank you very much.
Thank you, sir.
Thank you, sir.